We're going to do our last group of hypotheses tests today, but we're going to start it. There are 4 more tests, and 3 of the 4 are they're grouped together, and they do a lot of the same procedures. There's a little bit of difference between them. They're all called what we call chi-squared tests. And chi looks like a big X, but it's not. It's a Greek letter, and it is written like a kind of a curvy letter like this. And it is written this way. People want to say it's chi, okay, but it is chi, and it's the chi-squared test, okay. And the chi-squared is actually a new distribution. So far, we've had Z or normal distributions. We've had T distributions. And chi-squared is another type of distribution. The thing that was interesting about normal and T is they were both, in terms of the shape of the distributions, unimodal, symmetric, mound shape. They had that nice bell-shaped curve to both of them. Chi-squared is very different. Chi-squared shape of the distribution looks like this. It is definitely one-tailed. It is skewed. So it has a different shape altogether. It all has some things that are familiar to us, though. It talks about degree of freedom, much like a t-test has a degree of freedom, calculated a little bit differently, though. But the thing that makes chi-squared unique is it deals with counts, okay? I shouldn't say it's unique, because we're not talking about the average of something. We're not talking about the average length of a shoe, or we're not trying to find the difference between the mean verbal and math scores on an SAT. We're actually going to be talking about counts, a little bit like proportions, and sometimes you can do proportions and chi-squareds, and you can do one or the other sometimes. But when we're talking about like counts in terms of 3 out of 4 dentists prefer, okay? We would have counting 3 people out of 4, okay? So it can be written sometimes as a proportion, but oftentimes these counts are represented in a table format. Remember those contingency tables, or those two-way tables that we did a long time ago? We're going to be looking at information provided sometimes in that format. They can be two-way, or they can be a one-variable table. Table format. Okay? There are 3 different chi-squared tests, and we're going to cover, I think, depending on the time, 2 of them today. The last one is the chi-squared test for independence, and it's actually a little bit more involved. So we'll do that one on Thursday for sure. Okay? Kind of like if you think about, if you remember when we did two-way tables a long time ago, we talked about the probabilities and how would I use probabilities to show that something is independent of something else. Do you remember that? Where we talked about the probability of A and B is equal to the probability of A times the probability of, times the probability of B given A. Does that familiarize you guys? Look familiar, sort of? Okay, hopefully you've at least seen that before. It's been a while, but we'll kind of get back into our review here in a little bit. But we're going to look at that from a hypothesis test viewpoint through that lens on Thursday, okay, rather than the probability standpoint that we've done it from before. But the kinds that we're going to talk about today are, which one am I going to start with? The goodness of fit, okay? So the goodness of fit test, or I abbreviate it GOF, but it is goodness of fit. And then we have, and I always say this wrong, I think it's homogeneity. Is that how you say it? I believe homogeneous, but it's homogeneity. I think that's how you say it. Okay. So there's 3 different tests. These 2 use the same function on your calculator, okay, but their hypotheses are written differently. And this one is its own little bird, okay? So we're all using the distribution of chi-squared. There is a chi-squared CDF, much like there was a T-CDF, much like there was a normal CDF. So all the functionality is there. It's just a matter of which test am I performing, okay? And if you look at your calculator, go ahead and go to the test section, goodness of fit. And we're going to start with that one today in just a minute. But if you go to your test, you'll see if you scroll down, there are two different chi-squared tests in options C and D on your calculator under the tests. Erica, honey, I need you to put your head up, okay, if you're going to be here. I can't have you sleep. So the goodness of fit test is the one we're going to be looking at today, which is option D, okay? So we're going to look at that a little bit more closely. But let's go ahead and deal with just this guy for now, okay, the goodness of fit test. What does that mean? What are we talking about? Give me some context here. The goodness of fit test is really used to figure out whether or not a distribution differs from that that's predicted by a model. So when I say, well, we'll look at some examples in a minute. Predicted by a model usually assumes values are equally distributed or provides a historical population values. So either typically Mrs. Macker's distributions of A's, B's, C's, and D's in AP Stats is this. But this year it's this. Is it different? Does that make sense? Does that make sense what I'm saying? That we got different categories that we're looking at. We're looking at, does this vary from the historical distribution, or you could look at values differing from one to the other, and we'll look at that in a minute. The only conditions we have to worry about, there's two of them. We have to make sure that, well, obviously that it's random, and that the expected counts are 5. And we'll talk about what does it mean by expected counts versus real counts and all of that in a minute. But expected counts are 5, and I'll show you how to find those in a minute. And again, we're talking about counts, okay, not proportions. We are talking about values, okay? And it should be one sample. If you're dealing with two samples, then we're not chi-squared right now, okay? Or at least not goodness of fit. So one sample, and it's divided into categories. A's, B's, C's, D's, categories. Blue hair, green hair, red hair, yellow hair. I don't know, making stuff up, okay? We're talking about categorical data. That's important. Okay. Good so far? Nope. So categorical data from one sample, we're looking at, does it vary from a historical population or they're equally distributed among the values? Could be that too. Right. Here is the formula, and I do believe it's on your formula sheet. Brian, check it for me, make sure it is. I think it's there on the bottom right, maybe? Chi-squared value, observed minus expected squared. It's there. So it's on your formula sheet, so that's good news. Okay, so it's not something you have to memorize. But we have to talk about how to calculate it. And we're going to calculate it by hand a couple of times, but then we'll go ahead and use it. This is the test statistic, okay, this chi-squared value. So this is how you would calculate the test statistic. Remember, it was a t value before, or it was a z-score before. The sum. So we're going to look at our observed minus our expected value squared divided by expected. And I'm going to tell you what that means in a minute. And then we're going to sum all those cells up. Okay? Notice when we're talking about the degree of freedom, it's still n minus 1, but n is not the number of things, n is the number of categories. So it's not your population, it's not your sample size minus 1, it's the number of categories minus 1. Okay, so that's a little bit different. And we already talked about what the conditions were. Remind me what they are? Random, always, and which ones? The expected count. Yeah, the observed doesn't matter, but the expected has to be less than, or has to be greater than 5. Okay. So let's look at an example. Well, in a minute, let's talk about the hypotheses. The thing that I love about chi-square tests is that their hypotheses are always the same. It's always going to be, for a goodness of fit test, I'm going to say this, but give the context of the problem. Okay? The sample distribution doesn't differ. That's the claim. Okay? It's not any different than the historical distribution. percentages of A's, B's, C's, D's, and F's is still the same. The alternative is that it's different. This is a really smart class. I think there's going to be more A's in this class than I've had in the past. That's what we would think. That would be the alternative hypothesis. Okay? Not on that last quiz, but maybe overall. We'll see. All right. So let's look at this as an example. Okay, there's our first example that we're going to look at. So I have a biology professor that reports her historic calculation of grades has this distribution. 15% of the class usually has A's, 30 B's, 40 C's, 10 D's, and 5 F's. Okay? However, this is the distribution in the most recent course. Is it different from her historical distribution? So A, let's make sure we recognize this as a chi-squared goodness of fit test. Do I have categorical data? What are the categories? A, B, C, D, F. How many are there? So what's the degree of freedom? Okay, so the degree of freedom is 4 because it's the number of categories minus 1. We recognize it as categorical data. Why is it a chi-squared goodness of fit test? Well, go ahead. My observed data is what we see here in that table. That's what I observe. And then we're going to have to find our expected. Okay? What do we expect to happen? So we're going to create an A, B, C, D, and F. And we're going to find how many would I expect to be in each. How do you suggest I create those? Go ahead, Zachary.
Add up all, so I'm guessing
the total of people. I don't know what that is off the top of my head. Uh-huh. Okay, thank you. 325. I'll trust you on that. So the total people in her class was 325. Good. I'm going to find the 15% of that, 30% of that, etc. So that'll be our expected counts. It is okay for expected counts to be decimals, by the way. Okay? You don't round them. So we have 15% of 325. I got 48.75. I'm just going to write it this way. Not when it's expected. It's kind of like a mean. You don't ever round that either. Observed, obviously. You're not going to observe 0.75 of a person. But your expected can be a decimal. Okay? So 325 times 30. Okay. And again, I'm just writing sideways so I can fit it in. And then 40%. Exactly. That's nice. And then 10%. And then 5%. And we should be able to add all of those up and get the same 325. Do you agree? Just found the percentage of the total that we were given. That's all. So I have some observed values. And I have some expected values. Let's check our conditions. We know we're going to do, we should get into the habit of this because it isn't on the rubrics that we've come across lately. Aren't we supposed to be naming our tests? So let's do that. So this is going to be the chi-squared goodness of fit test. And let's check our conditions. There are 2 of them. What's the first one? That my observations were collected randomly. I don't know that, but what could I say? That hopefully it's a representative sample, right? Okay, and then what is the second condition for a chi-squared goodness of fit test? That the expected counts are greater than 5. Are they? What's the smallest expected count up there? 16.25. Still greater than 5, right? So all expected counts are greater than 5. So I've met my conditions. Yay. So what's going to be my null hypothesis? Be more specific in context. What's they? The grades. Use context, okay? So her grades, her current observed grades, do match, right? There is no difference, right? So go back and look at that. There is no difference. Does not differ, right? So her current class has the same distribution as historical distributions. Her current class's grades are no different. And then the alternative would be her current class's grades are different. Okay? This is not necessarily going to tell me right now. I'll show you on Thursday, but right now you're not going to know, is there more A's, more B's, more D's, more C's, more F's? Is any one higher? And there is a way to show that, and I'll show you in a minute. Yes? No, you're going to find a p-value. You're going to find the probability of the sample happening by chance. We're actually going to do it, perform it using the actual chi-square distribution. So let's just continue on. So we've named our test, we've checked our conditions, we've done our hypotheses. What's the next thing that you do? The test statistic, performing the test. So to do that, if you remember the formula for the chi-squared test, it's going to be your observed minus your expected quantity, it's the sum of that, squared divided by your expected, right? So let's look at how I would calculate this by hand. The observed for A's is 89. So I'm going to say 89 minus 48.75 all squared divided by 48.75 plus, because we're summing it, right? So I'm just looking at my A's. Subtract them, square it, divide by the expected. That's it. Now I'm going to do the same thing with my B's. 121 minus 97.5, quantity squared, divided by 97.5, plus, we okay with what I'm doing? Is using the formula, observed minus expected squared. So I've done A's and B's, now I have to do C's. So 78 minus 130, quantity squared divided by 130. We okay so far? Plus, then we have to do D's, and then we have to do F's. Hunter, you're not going to sit in that chair anymore if you're going to sleep, period. So D's is 25 minus 32.5 divided by 32.5. And then the F's were 12 and 16.25. And we're going to add those up. Huh? Oh, there's a shortcut. You know there's a shortcut. Come on. What, babe? Okay, that's fine. Evie? Yep. How you doing? All right. So what we're going to do is we're going to go ahead, and if we want to perform a goodness of fit test, I can show you. You can get a calculator. You can add all that up and find each value, and, you know, more power to you. Please do that. I might ask you to show me that work at least one time, okay, on how you can calculate the chi-squared value. But we're going to go down to the goodness of fit test, and I want you to look at what information it's asking for you. It's asking for some information. What is it asking you if you look at what the calculator brings up? The observed and the expected. So I have to actually put those in. Okay? So I have to go ahead and put in the two tables, as Devin already has done, which is great. So if we go to list 1, we're going to type in the 80, the 120, 178, 89, 121, 78, 25, and 12, right? And then we'll go ahead and do the list 2. And you can put these in any list you want. You can just tell the calculator wherever you put it, which is fine. So we're good there. And now we're just going to go ahead and perform the test. Once you have your observed and your expected, the calculator will do everything for you because it has this formula already plugged in. Okay? So stat calc, and we'll go down to, sorry, not right stat calc, stat tests. And we'll go down to the chi-squared goodness of fit test. What is our degree of freedom? So we're going to put that in. Okay? Why it asks that from you if you have, you see what I'm saying? Like, I don't know why. It should know that it's for, right? But whatever. And then we're going to calculate it. Okay? I have a chi-squared value of 62.5. The thing about chi-squared values is it's not like a z-score, where if it's greater than 3 or less than -3, it's really unusual. That doesn't really happen so much with chi-squared values because the degree of freedom can vary so much. But that is your test statistic. Okay? Then what do you notice about your p-value? Is it 8.84? Is it 8? What is that? What does the E mean? Very, very small, right? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 8, 5. Tiny. So just like before, if we have a p-value that's really tiny, what do you notice? We're going to do what? Reject that bad boy. Or reject your null, right? Reject that null, and therefore in context, what can we say? In context of the problem. The grades, her distribution is different this year. Okay? Now, what's nice is that we can actually say why it's different too. But we can say that, you know, her class distribution is different. And we have evidence to suggest that. If you look at the output of the calculator, that CNTRB, I don't really know what that stands for, but what I do know is if you scroll over, those numbers that are there are actually the parts of the chi-squared test statistic that you're adding together. So in other words, this first value here is 33.23. And if I scroll over to the right, all it does is give you a little space. The next one is 5.66. So this value right here is 5.66. In case you needed to know that for any reason. Okay? Yes? Uh-huh. Yes. Well, that's what this is. I just don't know what it stands for is what I mean. I know what it's calculating. I just don't know I don't know what CNTRB stands for. I know that it's calculating each of these cell values. I get that. But I just don't know what it stands for. If you find out, let me know, Devin. I just don't know what it stands for. Yeah. All right. I don't know.
Oh, I went back to this.
Yep, I see. I don't think it was. Yeah, you're right. Okay, and so show me what you did. I'm going to pause the recording. I don't care about this. But I want to make sure at least I got through introducing the idea. You're going to read about it over the. Oh, put your phone away, Daniel. Really? Oh, you were looking at what I meant? Okay. If you find it, let me know. Contribution? I'll have to look it up. Look at that. I'm not sure how that applies in this case, but maybe. All right, so we're going to go ahead and I want you to read chapter 26. It does talk about the goodness of fit test. It also talks about the test for homogeneity and the test for independence. It has all three in chapter 26. So you're going to read about all three. I do want you to do the just checking. And I'm actually going to assign one of the problems that we know ahead of time is the goodness of fit test, if I can figure out which one it would be. Let me see. Most of these are not goodness of fit tests. Okay, I'm going to have you do number 10 on page 629. I'm telling you in advance it's a goodness of fit test, okay? It says, do the patterns, do the numbers show up with equal frequency? I believe that's true. Oh well, try number 10. We'll leave it at that, okay?